Okay, let us discuss this problem. So in this problem we have to find the concentration of NH3 for a given solubility. So solubility is given, and then you have to find out the concentration of NH3. So let us say question says determine the concentration of NH3 in a solution whose 1 liter can dissolve 0.1 mole of AgCl. So let us say I have a solution. This solution contains NH3, and what we are doing is, so basically if I put AgCl solid, so if I put AgCl solid inside this solution, so this is a AgCl solid, so I have a solution of AgCl solid and NH3. So AgCl solid is basically dipped into the solution of NH3. What will happen? AgCl will dissolve, and the question says in this solution solubility of AgCl is 0.1 mole. So solubility of AgCl that is given to you, that is 0.1 mole. Very small, not a small solubility, it's a very high solubility. Ksp for AgCl is given, this is 10 to the power minus 10, and Kf for, so this is Ksp for AgCl, and you have been given Kf for AgNH3 whole twice plus. So Kf is given for AgNH3 whole twice plus, and this value comes out to be 1.6 into 10 to the power 7. You see, if nothing should be there, what should be the solubility? Solubility will be very low. So if nothing would be there, AgCl will dissolve, Ag plus and Cl minus, and this solubility is S, this solubility is S, so S square is 10 to the power minus 10, so S is 10 to the power minus 5 mole per liter. So you see, in 1 liter solution, 1 liter 10 to the power minus 5 mole will dissolve. So I can say in 1 liter solution, 1 liter neutral solution, only 10 to the power minus 5 mole will dissolve. But now if you see this question, what is the mole of AgCl that has dissolved? 0.1 mole, that is excessively high. How this is possible? This is possible only if, that is Ag plus that is coming after the dissolution of AgCl and Cl minus. So Ag plus reacts with the NH3 in the solution. So you see what is happening in the reaction vessel. You have AgCl, this will give you Ag plus and Cl minus. So this is equilibrium. Ksp is given to you. Now this Ag plus can react with NH3 into the vessel, 2 NH3, because formation constant is given for AgNH3 whole twice plus. So I can write AgNH3 whole twice plus, and the formation constant is very high, 10 to the power 7. Like this equilibrium constant is, so formation constant is very high, so this means this reaction has a tendency to go this side. So this means solubility will increase because Ag plus that will be dragged from this reaction. So due to the formation, complex ion formation, solubility increases. Are you getting? So solubility increases in this case due to complex ion formation. Solubility increases due to complex ion formation. So there should be A. Increases due to complex ion formation. Are you getting? Now let us say if the solubility is 0.1 mole, so this is given in the question, solubility is 0.1 mole. So this means AgCl has dissolved 0.1 mole of Ag plus and 0.1 mole of Cl minus. This is the solubility means. But this 0.1 mole will further react with NH3 and it will form AgNH3 whole twice plus. So now Ag plus will not remain as 0.1 because most of them, so let us say by reacts, I will not follow the reaction table, I will use the different kind of method. So you will have Ag plus here will have 0.1 minus bi, and he will have here bi that will be formed. Now see, so this means Ag plus is not 0.1, it will be different, but Cl minus will remain as it is 0.1 because Cl minus is not used in the reaction. So now if I know the Cl minus, I can calculate the Ag plus, because Ag plus into Cl minus is nothing but Ksp. Are you getting? Now Cl minus has to be 0.1, it has not reacted with anything else, so Ag plus into 0.1 is equals to Ksp. Ksp value is given to you, that is 10 to the power minus 10. So from here you can solve for Ag plus. Ag plus comes out to be 10 to the power minus 9. So you see, in the reaction vessel, concentration of Ag plus is only 10 to the power minus 9. Are you getting? Now if you see this reaction, so where this all Ag plus has gone? So you see, Ag plus came 0.1 mole, but now in the reaction vessel you have only 10 to the power minus 9 Ag plus. So concentration of Ag plus is only 10 to the power minus 9. So where the all Ag plus has gone? So this means 0.1 minus bi is equals to 10 to the power minus 9. So this means bi is approximately equals to 1. So if I solve for bi is 0.1 minus 10 to the power minus 9. So I can say bi is approximately equals to 0.1. Are you getting or not? This means almost all of the Ag plus that has been basically soluble from step 1 has gone to this form, complex. So this all the Ag plus that has been dissolved is basically complexed. So I can say here all Ag plus that has been dissolved forms the complex. That has been dissolved forms the complex. Are you getting? So this means now I know the concentration of AgNH3 whole twice plus, that is basically equals to bi, and bi is approximately equals to 0.1. So now if you see the second equilibrium, that is the Ag plus 2NH3, this forms AgNH3 whole twice plus. I have to go fast. This is Kf. Now this concentration is 0.1, and concentration of Ag plus we have already used in the first part. You see your copy, you will find this is 10 to the power minus 9. You can basically check your notebook. You see here you have Ag plus is 10 to the power minus 9. So now I can solve for NH3. So Kf is written as concentration of AgNH3 whole twice plus divided by Ag plus into NH3 concentration raised to the power 2. So from here I can say NH3 concentration raised to the power 2 is equals to AgNH3 whole twice plus, and this is 0.1. We have already said this is 0.1. So this is 0.1, and Ag plus is 10 to the power minus 9. And Kf divided by Kf. So you see what is the Kf? Kf you see we have already written, you can verify your copy. This is 1.6 into 10 to the power 7. So 1.6 into 10 to the power 7. So what will be the value? So this is 10 to the power minus 9 and 10 to the power minus 7. So 10 to the power minus 2, and this goes up. So 10, let me write here. I will have NH3 raised to the power 2. 10 to the power minus 2. This goes up, so 100 into 0.1, so 10 divided by 1.6. So concentration of NH3 will be root of this. So root of 10 by 1.6. You getting or not? And now I can solve for this. So this is 10 divided by 1.6. This comes out to 6.25. I have to take the root of answer. This is 2.5. So good. So this is 2.5. So concentration of NH3 that is required in this solution is 2.5. Now if somebody want, he can solve the same equation in the other way around also. So you see AgCl, it forms Ag plus Cl minus, and another reaction you have Ag plus 2NH3, and this forms AgNH3 whole twice plus, this is KSP, this is KF. Now you see, we can use this adding equations, because Ag plus in the solution is only 10 to the power minus 9. What is the concentration of Ag plus in the solution? 10 to the power minus 9. This means almost 0. This means the Ag plus is coming is 0.1 mole and I have left only 10 to the power minus 9. So most of the, so 0.1 minus 10 to the power minus 9 has already gone into the AgNH3 whole twice plus. This means almost AgCl that has been formed has gone here. So this contains 0. So I can say almost that has been used, produced by the first step, used by the second step. I can add these two equations very easily. And AgCl is basically solid. So now I will have AgCl solid plus 2NH3 and Cl minus plus AgNH3 whole twice plus equilibrium constant will be Ksp into Kf. Ksp into Kf. Now concentration of Cl minus will be 0.1, you know, because Ag plus is equals to Cl minus, and concentration of AgNH3 whole twice plus is also 0.1. Are you getting or not? Let me explain again. So you see, I have said earlier, all the Ag plus that is coming. So in the first part, you see, let me show you the first part. So you see, I said 0.1 mole of AgCl dissolves. This means Cl minus that comes into the solution is 0.1 mole. And Cl minus is not going anywhere else, so it will remain as it is, 0.1 mole. And by value is so small, so Ag plus is 0.1 minus by is so small, so I can assume Ag plus is 0. So this is almost all Ag has come here. So that is 0.1. So if I plug these values, I can solve the same equation again. Are you getting? So 0.1 raised to the power 2 divided by NH3 whole square, and this is equals to Ksp into Kf. So if you solve from here, you will again get the same value for NH3. So NH3 is nothing but a root over, so 0.1 divided by root over Ksp into Kf. Are you getting? So root over Ksp into Kf, and you know the value of Ksp and Kf, you can calculate the exact value in this case. So try to solve for yourself. So let us say NH3 divided by 0.1, and Ksp is 10 to the power minus 10, and Kf is basically, you have Kf is 1.6 into 10 to the power minus 7 plus 7. So what is this value? So 10 to the power minus 7 and to 10 to the power, so let us say put it like something like this. So 10 to the power minus 3. So why not we make 10 to the power minus 4? So this is 10 divided by under root 16. 16 is simply 4. So 10 divided by 4, so that is 2.5. Are you getting or not? So you can calculate this. So this is a calculation part. So you see, once again we have said there are two ways to solve the complex ionic equilibria plus solubility equilibria. Either you can use the first method or you can use the second method. In the first method, you are basically using a reaction table. You are setting a reaction table and you are trying to visualize the two equilibria separately. You are looking at the first equilibria, you are looking at the second equilibria. Using the first equilibria, sometime you are able to find something and that something that is found in the first step you can use in the second step. In some time both reactions will be basically coupled. You cannot solve either exactly one or two. You have to have both equations. You have to use the both equations. In this case, you can solve for Ag plus using the first equation itself. But in some other cases, you cannot solve Ag plus from the equation 1 only. You have to use the both equations. This is the one way to solve the problem. Another way is, since the second equilibria is very fast, equilibrium constant for Kf is very high, so second equilibria is almost goes to completion, and first equilibria is very small equilibrium constant. So I can add the two equilibrium constant and add the two equilibrium constant, two reactions. And if you add these two reactions, so this is one reaction, this is two reaction, you set a overall reaction. And once you set the overall reaction, try to write all the concentration and then use the equation for equilibrium constant. You will get the answer. So last problem and this problem, we want to say only one thing. If you have a solubility equilibria that can be coupled with another equilibria, something like complex ion formation equilibria, something like acidity H plus and Cl minus equilibria, that is reacting with H plus, that is again the reverse of K, acidity. So either you can use the second equilibria that has a K very high. In those cases it is easy to add the two equations and solve the equation easily. We will discuss some more problem of this kind. So only one concept you have to remember: how to solve this kind of equilibria. You can add the two equations. You can add the two equations and then you can solve easily. This is the only point I want to say. We'll discuss the next problem. Maybe of something of this kind of problem you'll see in the exams also. These are very, very tricky problems. If you don't know the process, it will be very difficult to solve in the exam. Okay, let us go for the next problem.